Sí, dime Patricia. Ocupado porque en 15 minutos empiezo una reunión. No, por la mañana necesito trabajar. No, no, claro que no. Dime, ¿qué pasa contigo? Sí, ¿cuál cosa? Ujú. Ah, depende, si lo pagas en 30 días no te cobra nada. Ujú. Pero tú sabes que lo puedes poner también al gobierno cuando pone la income tax return. 3.500. Yo lo sé. Bueno, no tengo este dinero, mi amor. Porque necesito ayudar a otra gente y otra gente y otra gente. Y ahora no tengo. mi hijo, tú sabes, con su apartamento, viene la mujer, llame de Rumanía a sus padres que viene por aquí, pagué la tarjeta de avión. Ellos regresar a Rumanía con ellos, de vacaciones, y todo con todo fue mucho, mucho dinero. Este es el problema. Ah, sobre eso tú sabes que él no tiene un trabajo bueno para pagar lo que necesita, entonces yo necesito pagar por él. Y ella trabaja también, una trabaja así para cuidar niños, tú sabes, muy poco que lo paga. Y así es la cosa. Oh, sí. Y ahora, ¿qué le podía decir? Que no viene sus padres para ver la mujer Simona, tú sabes. Bueno, viene. Ya, ahora 22 de mayo está aquí, hasta el junio. Sí, el 8 de junio se regresa juntos los cuatro. Su padre, sí, los dos, sí, se va para Rumanía. Sí, es bueno, pero a veces que Eduardo necesita tiempo por él. ¿Qué hace? Sí, ¿qué hace Sofía? Ujú. Le gusta, ¿eh? ¿Y tú? ¿Tú no quisiste? Ujú. Sí. Discúlpame mi vida, entonces esta es la situación. Por momentos, sí, sí. Si podía, claro, pero no puedo. No, no, tú no necesitas tener pena, es solamente que cuando puedo, puedo, cuando no, no. Yo te lo digo como es. ¿Entiendes? Bueno, de nada, de nada. Esperando que posible te veo un día, por aquí o por allá. Cuando vienes, sí, 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 a Toronto. Bueno, cuídate, besito, besito Patricia. Chao, chao, chao. Hi Peter, do you hear me? Hello? 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 Do you hear me? Hello? Hello? Hey, Hirtiza, what should they select here? Because this doesn't work. Like this is the headset here, right?
Yeah. DT.
So
Is that your headset?
maybe.
DT.
Yeah. Do you hear me?
speaking it up.
Hmm?
It is picking it up.
Yeah, the microphone, but I don't hear anything. Speaker.
Oh.
So the microphone works. Internal microphone array.
Let's see.
Oh. How about I disconnect this?
Yeah, try it.
Hello? Hello? Do you hear me?
I'll try talking again.
Can you connect to the meeting that I have? You have invitation.
Oh, that's the virtual.
Yeah. Hello? Yeah, definitely the mic is working. Yeah.
Yeah, talk like or Ed.
Okay, so you hear me, right?
Yeah.
How about now? Just a moment. Yeah, now nothing, huh?
No.
I can hear you. But not the microphone. How about now?
Nope.
No? And now?
No, but I could just a second ago.
Yeah, it's okay. I will go without. Just a moment. So do you hear me?
No.
Wait. Right now? You hear me?
Yeah.
All good, right?
Yeah.
Okay. Okay, so it's all fine. Can you talk back to see that I hear you?
Yeah.
All right. That's how I'm gonna do it without the headset.
There's a bit of buzzing. I don't know.
Is that gone now?
No.
How about now?
No.
But you hear me, right?
Yeah.
It's just a little bit of noise.
Mm-hmm.
Okay. We will go with this. Well, I was hoping to get more attendees, but it looks like there you go. Some more people. Do you guys hear me?
Yeah, we can hear you.
All right, so the topic today is variable frequency drives. And the reason I'm doing this webinar is because around the plant we have many applications with the VFDs, and definitely some of them are not completely understood, or the VFD is not properly set up, or altogether the finding is that the VFD is not really the box that is used, and instead of the VFD actually we have another box that is, for instance, a soft starter. Please do not hesitate to put questions and interrupt me whenever you want. I will go over the slides, but really I have also a manual that is like 100-page and is all the information you need to know about VFDs. So variable frequency drives are used for speed change of the motor, induction motor typically. So what we're talking about here is induction motor speed change. Very well can be used for other type of motors. For we have drives for DC motors, we have drives for synchronous motors, but most of the time when we talk about VFDs, those are variable frequency drive, and they are for induction motors mostly. In the plant we have applications for different fans and other things that are need to have variable speed, also variable torque. So the objective of this is to understand how the induction motor works, the installation, characteristic, VFD types, interaction and settings of the VFD, torque control and speed control. So really the VFD can do many things, and depending on the type of VFD you can have a torque control, a speed control, or even a position control. Example where we need a position control is on the fuel handling, where we want to have the bridge correctly positioned to actually fill the tubes in the calandria with new fueling. So that's a precise positioning that is done with VFDs. In this case, the VFD will move around from one motor to another, so will be used for different motors. And that's where you need to pay attention if the VFD is properly set up, especially if you have a VFD that is not a simple volt per hertz type. So if it's a scalar type, volt per hertz, the settings are pretty easy to achieve. But if it's not, and is actually a vector control or director control, then you need to have certain steps in mind, like parameter identification of the motor. So we will go through this, and I will explain what's the difference and how we can set up properly the VFD if we use a VFD. What's the difference between soft starter and VFD, and then what is a full Regen drive, active front end drive, and so on. So we have different types, and also we have the major two classes, which is motor starter, soft starter, or VFD. Any questions up to now? Any questions? Yeah, I hear no questions, so we go forward. Types of motors, as you know, DC and AC. I don't think we have many DC motors in the plant. Most of them are AC, and as I said, the AC motors are induction squirrel cage. For special applications, we can use servo systems. And that's a question really to ask yourself, if you have to position something precisely, if you should use an induction motor, for instance, for the fueling machine, or you should just go with the servo system, because the price of the servo system today is not much different from an induction motor system. So basically for the same price you can have a servo system, and the servo system is having many advantages over induction motor. For instance, the servo system can start and stop all day long, will not overheat. A servo system will have software that is easy to control positioning and to write code for different movements, as opposed to an induction motor where you need to do everything by setting up the VFD and eventually to add a PLC, a programmable logic controller, that will take care about the different commands to the VFD. So that's the classic way, the way it was done all along. So we will go over this as well. So in order to start the discussion and to understand what is the difference between the VFDs and these machines control that we talked about, including the servo, please remember that the electrical machine is an electromechanical converter, so it can operate, the same equipment can operate as a motor, a generator, or a brake. So when we supply electric power and deliver mechanical power to the shaft, that is a motor. When the mechanical power is supplied to the electrical machine, is delivering electrical power and is a generator. And intentionally I put the generator this way because a larger diameter will help a generator to actually maintain the speed and maintain the 60 Hertz. Either in case of a motor you want to have a low diameter, a longer body, in order to get the motor changing speed as fast as possible for different applications. And then the brake is when we command the electrical machine to go forward, reverse, but we stop in the 0 speed. So actually reverse 2 leads on the induction motor. The motor, if you leave it with the leads changed, will form a reverse rotating field and will go in reverse. But if you just want to stop, that is emergency stop, is plugging. And reversing the 2-phase will generate a reverse field, which the actual cage and the rotor will follow with a full stop. So you disconnect the power once the full stop is achieved. So any electrical machine can be motor, generator, or brake, depending on the way it's used. Now we know the construction of it may be different. So the motor, as I said, has a low diameter and long magnetic core for achieving the volume, because the volume of magnetic core gives the power, is proportional with the power. So you need a certain volume of magnetic core for a certain power output. And the power on the motor, on the nameplate, is the power that you have on the shaft. So it's the mechanical power. So when you're talking about a 30 horsepower motor or a 50 kilowatt motor, that is the actual mechanical power available at the shaft of the motor. Generator, we have many generators. We have the EPGs, SGs, the main generator. Those are with primary source is the turbine, or generator is the actual CTU machine which connect to the generator, which in this case is called alternator. And then the braking is used by starting and stopping for different applications that we have with these electrical machines in the plant, like fueling machine system. Precise stopping, we don't want to break anything mechanically. Any questions up to now? Yes? No? I will not go through much of a theoretical part. I will just go with one equations here, that is the electromechanical converter, that we said electrical machine is a electromechanical converter. Either is converting electric to mechanic or mechanic to electric, and this is the actual balance between the mechanical and electrical power. The inertia, the total inertia of the shaft, multiply with the variation of shaft speed, equal the electromagnetic torque developed in the electrical machine minus the load that is attached to the shaft, right? So in any situation, if it's working as a motor, a generator, or a brake, this is still valid. So this is the general equation of any electromechanical converter, which is the actual, in our case, motor. Induction motor types, we have two. The squirrel cage 90% of the time is because we want to have a motor that is robust, no brushes, no other elements that can break down the motor. But the disadvantage of this motor is that you only supply power from the stator, so you need to have a very short, very small air gap. So the squirrel cage bearings and everything else need to be very well maintained and aligned, otherwise is a danger of touching stator to rotor. And then we have the wind rotor, that is with access to the rotor through brushes, and is a good control that you can actually change the parameter in the rotor, adding resistors to the external brushes. That's how you can change the speed and the torque, and is still used, but the preferred motor by far is the squirrel cage. Just a slide here to remind you, the squirrel cage looks like that, and this is internal. You see the stator, the windings with insulation, and the insulation class can be different, can be, according to NEMA standard, can be A, B, F, or H. H being the highest, NOMAX, 180 degrees above ambient. The lowest is A. We don't have A or B in the plant. Rarely we have H, so majority of our motors in the plant are class F insulation. Then the enclosure, that you have a IP rating. For instance, IP65 is 6 is for particles, and 5 is for gas and liquid. So different applications inside the plant, outside the plant, or if we have ventilation in the battery room, that need to be totally enclosed because you don't want to have explosion. We know that battery charging, the batteries we have are open, and they are producing hydrogen during charging, so we need to have enclosure that is rated for hydrogen. Then yes, you have the rotor. The rotor is also magnetic core, lamecoidal magnetic core, and you see that the bars are in contact with the magnetic core, the aluminum bars. And that's not a problem because the voltage in the magnetic bars are pretty slim, and the current will not flow much from the rotor to the magnetic core. But there is some of that flowing into the actual magnetic core and into the shaft, which generates some sparks in the bearings if you are not using some protection copper rings, or for medium voltage motors are the disc fiber optic that block these currents from penetrating the bearings and creating sparks. So you also see the cage has a certain slope, and that's because we don't want the rotor to glue to the stator. You have a rotating field in the stator, and the rotor will follow by creating induction in these bars. Each bar is a phase, a different phase, and then you have a torque developed between the cage and the rotating field. If they will be perfectly aligned with the shaft, is a possibility that will glue in a certain moment the direction of the current to be the same as the direction of the current in the stator, and then they attract each other, so they need to reject each other, so that will be in a reverse direction. That's why you have a certain calculated angle between the slope between the actual shaft and these bars. Now regarding the bars, there are 4 categories in NEMA MG1. You got MG1 classification, the design classification A, B, C, and D. A will be on the shelf, B will be on the shelf, as you see it in this picture. A will be high efficiency. What high efficiency means? That either it has copper bars, not aluminum, or the actual bars are inside the rotor, you don't see them, so the rotor is shiny outside and the bars are inside. Now this motor will have a high efficiency, as the name is saying, high power factor, but it will have less losses, but it will have less starting torque. So careful with the usage of high efficiency motors. It may not be the best. And yes, as far as I know, we replaced that motors in our plant for the fueling machine, and that need to be with reconsideration of the starting torque and the possibility to have recalibrated the VFD for that application, because an on-the-shelf motor will not be so sensitive in the vector control with the way it is as a high efficiency motor. Then you have class C, the deep slot for higher starting torque, but of course the efficiency and power factor goes down. And then you have the class D with double cage, that is the rotor actuators and all the actuators that operate on a high starting torque because they need to go against the let's say the water hammer in the certain applications. They operate only for less than a minute, like 47 seconds. They need to close a certain valve, D2O injection valves, and the action is done, but need to be guaranteed working, so we don't rely on VFDs in this application. We have double cage. Another special motor can be multiple speed motor for traveler screens, and that is done through multiple coils in the stator that is changing configuration to get different speed of the rotating field, and the cage will follow. For instance, for 1800 RPM, 2 pair of poles, we will have 1750, 1780 maximum rated speed of the shaft. Is always a slip between the rotating field and the shaft speed, because otherwise there is no induction in the bars. So that is the condition for the induction motor to work, to operate. The higher efficiency motors, they have a less required slip for the operation. The lower efficiency, like deep slot and double cage, they will have larger slip, larger losses. Okay, so any questions regarding the motor? So that's very in a nutshell, very rapidly going through the parameters and explaining what is inside. You also see on the shaft here on the cage some wings. Those are for cooling purposes, and then the little cylindrical sometimes holes in the ring, those are for dynamic balance. So in order to achieve a perfect dynamic balance, these little things are shaved off as required to get a perfect balancing dynamically. As we said, the air gap in these motors are no more than 0.5 millimeter. Okay, the stator power, considering a perfect sine wave, is like this. So the 3-phase, and that makes the motor creating the rotating field, because they compose vectorially. The 3-phase and the rotating fields will have the speed. The formula for the speed is 60 multiplied with the frequency over the number of pair of poles. In some books you have 120 multiplied with frequency over the number of poles, but it's the same at the end, because you have pair of poles. You always have a north and a south. You cannot have a odd number. Always is even number, so is worth it to work with the number of pair of poles. For instance, if you have 2 pair of poles, is 60, because is rotation RPM per second, rotation per second. So it's 60 because it's second, multiplied with 60 hertz over 2, and that is 1800. If we would be in Europe, then we will have 50 multiplied with 60 over 2, which is 1500. So the RPM in Europe is a little bit less, because the frequency is 50 hertz. Now there are constructions of motors that can work on both frequency, but watch the output torque, because it's also proportional with the frequency. It's not the same. So if you have actuators manufactured in UK at 50 Hz tested, you need to convert those tests to 60 Hz. So be careful with that. Alright, so the cage looks like this. These are the bars and then the two rings forming a short circuit, perfect short circuit. So the current flow through all the bars, and they slightly phase shifted, but they form together a torque, because the force goes in opposition for the diametral opposite bars, and that is the torque. So the force developed multiplied with the diameter of this cage is actually the torque developed, which is the electromagnetic torque that run the motor. Okay, induction motor squirrel cage design. We said already no insulation required because the voltage is very low, and the actual copper and aluminum are very good conductors compared to iron, but there are some little leakage currents that we take care of with those Baldor invented copper rings on both sides to protect the bearings. If you don't do that, the bearings will have a much shorter life. This one is the slip, right? So what is the slip? Is the difference between the actual speed of the rotating field minus the speed of the shaft, which is for relative percentage you can even have is divided by the rotating field speed. So like we said, 1800 minus 1750 over 1800, and then multiply with 100, we will have it in percentage. So that's usually a certain value on the nameplate. However, is changing with the load. So when you have a larger load, this slip increase. When you have no load, this slip decrease. Let's say if you have a slip of 1.5%, at no load maybe 1, at full load maybe 1.7. So it's not a constant value, it's variable with the load. Voltage and frequency variation. NEMA also is telling you that a motor should be designed as such when you test the motor is passing, so the three phase resistance should be in 5%, but it should accept variation of the three phase voltages, like plus minus 10% in voltages or plus minus 1 Hertz in the power supply, should not affect the performance of the motor. After that, yes, is derated with the voltage, with the square voltage. So a lower voltage is not linear. So if you apply half voltage to a motor at 60 Hertz, you will develop only a quarter of the torque, because it is proportional with the squared voltage. Okay, so keep that in mind. The torque is not linear with the voltage, it's proportional with the squared voltage. Service factor, you hear that very much in different applications. As we said, we have class F. Service factor, usually we have 1, so 1 is saying that it doesn't accept overload. However, in some applications you can order the motor higher than 1, 1.15, even 1.25. What that means, simply North American standards allow for a 15% overload or 25% overload without damaging the motor. For a 10 minutes overload with 15% is still gonna work fine. It's like a little bit of an oversize of the motor, so that's all it is, this service factor. Is in conjunction with a duty cycle. The duty cycle is the on-off timing of motor power. The best behaves a motor when it's continuously powered, and the worst when you switch the power on-off. The induction motor will overheat because the inrush current to the motor is around 9 times rated. So locked rotor current is with approximation 9 times full load current. However, for applications where we have to start on a black start, or the motor is connected to a UPS, we want a low inrush current motor, and that can be done by the manufacturer arranging the coils as such you got only 6 times full load current. So the low inrush current motors, they can achieve something like 6 times full load current, but there is no way you can get something that is less than that directly from the motor. So if it is cross connect to a power supply, the best motor can only do that 6 times full load current, which is a lot. It can trip different breakers and fuses. So what you do in application with multiple motors, you're gonna connect them in a staggering one by one. You will not connect them all at once. You will have a time delay and say, well, it is gonna connect each one in a half a minute or a minute, depending on how long it takes to speed up the motor. That's the actual process we have for the D2O injection valves. We have 8 valves, and we're gonna connect those one by one with a staggering of 1 minute apart. Right, so with this power converter, if you don't have questions, if you have questions about the motor, because now we're gonna go into the power converters. Any questions up to here? No questions. Then we're gonna review the power converters. There are 4 in total. So in the power electronics that can be used with motors, and in the actual drives, we can have rectifiers, which are the DC drive for DC motors. You have a rectifier that controls the speed of a DC motor by controlling the voltage on the shaft, on the actual armature. Very easy control. Chopper is the same use. Is gonna be if the input is a DC, like in traction, streetcar, subways, and trains, they will have a DC input, so you need to control the DC voltage on the armature of the motor for controlling the speed. Then you're gonna have a chopper, because the chopper is chopping the DC voltage, creating variable DC voltage on the output. So rectifier alone is a common DC drive that you find in different factories. For instance, Baldor has a very reliable DC drive that can drive the DC motor with high starting torque and torque control or speed control, but the problem is the brushes. Or chopper that can be used in streetcar, subways, and trains, and those are the variable speed obtained from a DC line, like the DC 27 kilovolts for the train, or 900 volts, 700 for streetcars and 900 for streetcars. So inverters are doing the reverse job of a rectifier. So it's taking a DC input and is converting it to an AC output. But by doing that, through the pulse width modulation process, reconstructing the sine waves, but in this way, the actually inverter creates also harmonics, because anything that is non-linear, like magnetic core, capacitor, saturated core, gives third harmonic. Chopping a certain wave with switching IGBTs, insulated gate bipolar transistors, in the inverter will create also harmonics. Now the total of the harmonics is called total harmonic distortion, and that's what heat up the motor. So when we have a VFD, we will use 2 out of these 4 converters at the same time. It's a double stage converter. We will have a rectifier that takes the AC input to a DC bus. The DC bus will have a capacitor bank, and the capacitor bank needs to be proportional with the power. And then we will have an inverter taking that DC back to AC and supplying the variable frequency and variable voltage. In the same time, the inverter will change voltage and frequency on the motor input. And yes, you need filters and you need to take care about the harmonics. Cyclo converter is not so popular. The cyclo converter is for synchronous machines and is changing only frequency. The output frequency can only be less than the input frequency, and is for large synchronous motors. For large induction motors, you have a VFD that is slightly different than the one described, which is a voltage type. There is a current type that instead of a capacitor bank in the DC bus has actually a coil that magnetize and keep the energy for the commutation of the IGBTs in the inverter, and that's for medium voltage inverters. Now the new ones, they also built with capacitors, so there are capacitor types, but you can still have the older type. For instance, Rockwell provides that, is manufacturing in Waterloo division. That's the power division of Rockwell, and they have PowerFlex 7000 series, which is current inverter is called, not VFD, so it's called current inverter, but indeed is actually a rectifier and an inverter with a large coil on the DC with an air gap to avoid saturation. The problem with this type of VFD with coil is that the coil need to be like 10 times the motor induction, so you need to change the coil if you change the motor type. So that's the big disadvantage of these current inverters. Any questions for the 4 power converters? If not, I will jump to the soft starters. Now, don't be confused with starters. So when we say motor starter is one thing, when we say soft starter is another. So the motor starter, as we know it, is an electromechanical contactor, a breaker, overload, all that part that is in a box in a MCC starter. But when we say soft starter, this one is electronics. So it has thyristors, or for low power you can have this 2 thyristors in one lower power. So this one is operating as would be a transformer, is not changing the frequency on the motor, is actually changing only the voltage. On low power, those are called triacs with two ACRs or thyristors in anti-parallel in one device. So what we do with this? We change voltage. Do we change the frequency? We don't. Therefore, a soft starter cannot have large torque. Remember, the torque is proportional with the square voltage. So when we start with low voltage, there is almost no torque. Soft starter decrease the inrush. So as opposed to have like 9 times, you can have on the shelf motor the inrush current decrease to only 3-4 times or even less, depends on the application, but may not be suitable at all for a harsh application because does not have enough starting torque. So be careful where you're going to use this. Soft starter is not a VFD, is a electronic implementation of a transformer or auto transformer. So 60 Hertz all the way, variable voltage applied to the motor leads. Now, after the motor start, another particularity of the soft starter is that you need to take this soft starter off. You cannot leave the soft starter in the circuit supplying power to the induction motor, because simply is gonna ruin the motor, because it has very high harmonics. So by chopping with 60 Hertz the sine waves, like half sine waves or stuff like that, you will inject a lot of harmonics in the motor. So there is no motor that can keep up with that. Soft starter is always with bypass contactor on each phase. So once the motor reaches the full speed, the contactor closes, and the soft starter through a logic can move to another motor to start if desired. It's typical for water treatment plants where you have to start up to 40 motors. You have the same soft starter moved around and you start whichever number of pumps you need. Okay, so once again, the face of this soft starter may be the same as a VFD. It looks 3-phase in, 3-phase out, and has LED displays, LCD display and keypad and network and everything else, but is not a VFD. And this is where people are confused by using this soft starter as a VFD, or trying to solve problems that are for VFDs and not for soft starters. Okay, VFD for a very low 2 horsepower motor. You see the blue capacitors are actually the DC bus capacitors, and then you have a main board that is on top of IGBT, 3 blocks, 1 per phase, and then you have a small piggyback board with the CPU that has the control. The main board with IGBTs has a power supply, and then you have protections and everything that is directly controlling the IGBTs, the gates and everything else. Okay, so it's very compact. This is a Yaskawa drive, very performance. Siemens, Yaskawa, Mitsubishi I like because it's lower price and has same performance or better. So there are manufacturers that are fully trustfully and with good record of VFD manufacturing, good OPEX. So this is the schematic, the power side of a VFD. You have the rectifier. If you don't mention anything, you're gonna get a VFD with diodes. That is your rectifier. And then on the DC bus, you see the capacitor, the charging resistor. Once the capacitor gets to 90% of the full voltage, you will close that switch. And the switch it will charge faster the last 10% of the capacitor, because you cannot change close the switch before. If you don't have that RC resistor, the inrush current will blow up the diodes or the fuses that protect the diodes in front. So you need to have a charging resistor and bypass the resistor whenever you are almost at the full voltage. Then you have a leg that is for braking. That is a resistor at the bottom with a IGBT and reverse diode that is usually on the outside of the drive. So it's dynamic braking resistor called, and only can take up to 15-20% of the power of the drive. You cannot have a full power resistor. Let's say the drive is a 50 kilowatts drive, you cannot have a 50 kilowatt resistor, but you will have a 10 kilowatts, maybe 8 or 10 kilowatts maximum. So this is a chopper. What's happening with this leg? Once the DC bus increased to 110%, because the motor became a generator, you are slowing down and you release power from the electrical machine which became a generator. If it's a large inertial load, that will take quite a while to stop. The power goes back to the diodes into the capacitor bank. So the capacitor bank will increase the voltage because the power has nowhere to go, and you need to dissipate that extra power by chopping this on and off resistor that is external, is a power resistor on a heatsink, and that way you get rid of the extra power and the voltage goes down. If you don't manage to do that, the drive will protect himself, and you will have a message of DC bus over voltage, and it will stop. So this leg is the dynamic braking in the DC bus, and the next is the actual bridge of 6 IGBTs with reverse diodes, and those are the actual inverter. So the inverter, as you see, depends on which direction we fire those IGBTs. We create a magnetic field in one direction, or in reverse if you change the reverse of the pulses. Is always 2 conduct on one side, on one or the other. And if we want, we can also perform the quick plugging by reversing the field in the induction motor. Also, what we can do is a DC injection braking by opening certain IGBTs permanently, like 2 on the top, 1 on the bottom on the other leg, and then you got frozen the magnetic field in the electrical induction motor. And if the magnetic field in the stator is frozen, then the cage will follow and will stop. So you have parameter to set up the DC injection braking, like how long you want this to take place and what is the percentage from 50% to 100% full current. So DC will be applied to the motor as opposed to AC when you do DC injection braking, and you can hear a noise clearly in the motor. So yes, we can do dynamic braking, DC injection braking, and plugging. What we observe here, the inverter is a 4-quadrant operation. It actually can absorb voltage and current one direction, but can reverse the direction of current charging the capacitor, and also can reverse the voltage on the motor by going forward reverse. So the inverter, it covers all 4 quadrants, positive, negative for voltage and current, but the diodes are 1 quadrant only. So that's the discrepancy in a on the shelf inverter VFD, because they are not even. So that's why we have other types of VFDs, as we're gonna see. Okay, and here is the 4-quadrant operation. There are 2 types, gravitational and horizontal, and this is how we need to think about this. You got actually 4-quadrant load, because the load is a 4-quadrant. It can go forward, reverse, it can go up or down in case of a crane, and then the actual current and voltage need to change on the VFD to accommodate that change in the motor with the load. So motor with the gearbox and the load behaves in a certain way, and we need to accommodate that with the VFD. So very important. If you don't order the right VFD for your applications, you are set up for failure. Your VFD must cover all the quadrants of operation for your applications. So VFD for traction, for instance, will be 4-quadrant operation, because the vehicle will go forward, reverse, will go braking when is regening. You can brake forward or brake in reverse. So Tesla and other hybrid cars, they all need to have a 4-quadrant operation converter. The motors in Tesla, by the way, is a brushless permanent magnet AC. Brushless because it's a higher performance brushless than DC, which is having all phases powered at all times. Active front end solved the problem with the VFD. So now, instead of using diodes, if you say I need an active front end drive, then your drive will have same configuration but different control type. The control on the rectifier will be as such. The capacitor banks are always fully charged, and you will need to have an input filter, because the input filter is the one that protects others from the power you're gonna generate back to the grid, right? So whenever the motor become a generator, it will actually inject power to the DC, and the DC synchronized to the grid will inject that power back to the grid. Any questions regarding active front end? So this is IGBT type drive and is available up to 250 kilowatts. If you need something that is more powerful, so higher power than that, then you will need to go for the full Regen Drive, the older technology that is available out there. When you're gonna need an extra box, you will have the inverter with IGBTs, but the rectifier will be thyristor type, and the reverse box will be attached as a full regen. So whenever the DC voltage goes up because the motor becomes generator, then the reverse thyristor start opening and synchronized to 60 Hertz will deliver power to the supply grid, except when the supply grid doesn't accept the power. There are exceptions. That's why you have other type of braking. So even if you buy active front end or full Regen Drive, you should have the other dynamic braking installed on the drive. Okay, protections on the drive: fuse, MOVs, electronic current protections. Now the fuse are for diodes and thyristors. They don't protect IGBTs. MOVs, metal oxide varistor, is for over voltages on the diodes or thyristors. thyristor or even IGBT, we need to know that IGBT is very touchy. It's gonna deteriorate in a pulse that is over voltage in 25 microseconds. So we need to have very fast protection. That's why there is electronic current protection in the inverter. We have RTDs, usually electronic voltage protections with snubbers as well, because the snubbers will control the over voltage. Is like the RC network that is in parallel with each IGBT, and that will bypass that energy, not letting it to go through the actual thyristor. So different type of snubbers, active and passive, but all the IGBTs will be protected by snubbers and also by the design of the drive. So need to have as short as possible DC bus for less leakage inductance. So let's review what we did on the power side. We have three types of drives. We have the on the shelf with diode rectifiers for common application. We have the active front end for regenerative drive that use IGBTs on the rectifier with force commutation, the new technology, but only available up to 250 kVA. And then we have the active regenerative unit. The regenerative unit is with an extra box that connect to the power whenever you have extra voltage on the DC bus, because the motor became a generator. All right, so with this slide we start talking about the control. If we have three types of drives for the power side, we also have three types of control. So the control can be scalar, simply volt per hertz, easy to set up, is usually open loop. It can be close the loop and get a better performance, but really you don't need to tune any regulator or do anything, just adjust boost, how much voltage you want when it's starting, auto boost, how much of the current you need to set up as a feedback and from the load. So the higher load, the higher the auto boost will help the motor to develop more torque. And then you have skip frequency for resonance. You have different curves of volt per hertz that are deviating from a straight linear, depending on the type of load. If it's a harsh load, you want more voltage. Then if it's a low load, it will be the other way curved, like exponential and logarithmic. So you can select the curve volt per hertz. Also you have different acceleration time, deceleration time for different applications. So all this can be set up in the Scalar. Also you need to have the catch frequency whenever you want to avoid the problem with restarting before stopping, so you don't get in opposition the induced voltage with the actual applied voltage. So all this is available in the Scalar. Again, there is no parameter identification and there is no tuning of any regulator. It's all settings and based on empirical try and error. Easy to set up, but does not have, the Scalar drive does not have torque control type and does not work for harsh applications with 100% full load applied at the shaft. It will give you trip on overcurrent or trip on DC bus over voltage, whatever, cannot handle full load torque on the shaft in a step manner. Gradually, yes, on a slope or in baby steps. So that's the Scalar. Then, because of the gap, in 1971, Rudolf Blaschke developed in Siemens the vector control and is performing very well today. So we have a vector control. Now the vector control is also called field oriented control, and this is what we have, for instance, on our fueling machine systems, is a ABB vector control drives. The key on the vector control, especially if you are using high efficiency motors as we do, is to have an exact match of the parameters of the motor in the drive, because the drive will calculate an equivalent DC model and will control the magnetization and torque independently. If using the DQ axis, D for field, Q for torque. If that doesn't happen, then the vector control will be performing even worse than a scalar, so will not be able to handle the load. And overheating and vibration, everything else. Direct torque control is variants developed by ABB, which it was developed in 1986 for torque applications. Is a simplified vector control, knowing where the acceleration need to go, is tabulated in the memory, and is less calculation required. So now when you order a drive, you can order a scalar drive as control goes, or you can order a vector. When you order a vector drive, the difference in price will be minimum, will be a couple of $100, because it's only intelligence in the drive that is extra. But you have the possibility to switch to vector if required, so your application doesn't handle properly the load with a scalar algorithm. You can switch to the vector algorithm and solve the problem. Not everybody provide direct torque control. For instance, SEV Eurodrive, Eurotrack has vector and scalar, but does not offer direct torque control drives. Direct torque control you can find from Siemens, Mitsubishi, Toshiba, Danfoss, even Schneider, they have direct torque control, GE. So all the big manufacturers, they will have all three. So if you order direct torque control drive, you will have all three, because it's like build one on top of the other. So direct torque control will have vector control and scalar. Now direct torque control you don't really need if you don't foresee a torque control application. What is a torque control application? I may want to control the torque in a certain material that you pull with the shaft, so you don't want to break paper or rubber or whatever, so I want to keep a constant torque at the shaft, and that's where the torque control kicks in. So if you don't foresee an application for torque control, you don't need to bother to order torque control, but I suggest for most of the application the vector will be a nice to have, and for things like fueling machine will be the one. So vector control must. An alternative in the case of the fueling machine is to use the servo. Servo is always vector and torque, so every servo system will have automatically incorporated vector system and direct torque control system, will not have scalar. So scalar is not part of any vector system, but the other two are there by default. Okay. Pulse width modulation. This is how you create pulse width modulation in the control, comparing a sawtooth with the sine waves, and then those are the pulses on the three phase, and you can see that the center pulses at the bottom are larger than the extreme in order to create a current. The sine wave that you see here is the current, so creating the current as close to a sine wave as possible. Now the motors that are running with VFDs, you need to order that motor as inverter rated, because they are designed as such they can take these harmonics generated and they not suffer too much, because they have reinforced insulation on the first few turns. On top of that, if you want to get lower harmonics in the motor, you can also use the Belden cables that are yellow jacketed cable with low capacitance, and filters. Actually the manufacturer will tell you that if you run the cable from the drive to the motor for larger than 100 feet, you will need to have a filter on the output, and that filter can be 3% or 5%. The 5% filter is a stronger, is measured the same as the short circuit impedance of a transformer, right? So tuning, yes, vector is always closed loop control and need tuning. after is doing the parameter identification. So first thing a vector control will do, it will read the motor by performing a cycle that is not under your control. You just say quick start and the motor will turn fast, slow, forward, reverse. After finishing the cycle of, let's say it takes few minutes, it will have all the internal parameters already read, and then it's going to correct with the temperature, the resistance, to have a good motor model in order to calculate the required control for the magnetization and torque. So that will be always there. Another characteristic of the vector is tuning. So most of the time, because it's a closed loop control, you need to do tuning, which means you need to match the regulators of the speed or torque with the process. If it's a proportional integral, the proportional will be correlated with the torque of the shaft, and integral with the inertia of the load of the shaft. That's why you put gearbox. The higher the ratio, the less the motor will feel the inertia change. So these are some waves here that is showing you the response after you apply a step. You will read the feedback of the motor, like speed, and usually we look for the middle one. We accept some oscillations, but not more than 4, and less than 4.7% overshooting at the first oscillation. PID rarely is used because derivative is picking up noise. Theoretically, it should be a better controller that lower this first overshooting, but people does not like it in the industry much because derivative can give you trouble. So this is the tuning, and is done with the step input and reading the feedback. Harmonics, you want more about harmonics, you can find in IEEE 519, and also in the tier, the Hydro One interconnection requirements is on the website. They took that from the standards. There are CSA 60,000 series with the harmonics and compliance. VFD installation, we talked about. You have breaker, filter, even a reactor for large inverters, and then you have input noise, DFD output, and the Belden cable. The motor must be inverter rated motor. And with this one we reach the end, so I will ask you if you have any questions related to VFDs, servos, motors, control, or anything like that. Or if you want, you can send me an email with the next topic that you would like to see. I will also mention that all these videos are on the PMC website. My page is with all the webinars that we had up to today. Any questions? I hope this helped, and if anybody want to have any discussions about, using soft starter wrongfully, or vector control that is not properly used and give trouble in the plant, we can definitely go in depth and discuss the situation with that application. If no questions, then I thank you very much for attending, and I hope to attend next one, which will be in a week from now. Thank you. Have a nice and productive day. Thank you, everybody.
Thank you. Thank you.